Hello friends, I welcome you in lecture number 4 on normal distribution. In this lecture we are going to discuss examples on normal distribution. So let us start with example number 1. Suppose that the current measurements in a strip of wire are assumed to follow a normal distribution with a mean of 10 milliamperes and a variance of 4 milliampere square. What is the probability that a measurement exceeds 13 milliamperes? So here this is the example of normal probability distribution. It is given that these current measurements in a strip of wire follow a normal distribution. So the variable under consideration is nothing but current measurement. So first we have to denote this variable by capital X, and it is given that mean of this random variable is 10 milliamperes and variance is 4 milliamperes. So we first start with capital, we denote the random variable current in milliamperes by capital X. So it is given that capital X is a normal random variable, and also it is given that mean of capital X is 10 and variance is 4. So if sigma square is 4, standard deviation is sigma equal to 2. Now we have to find the probability that measurement exceeds 13 milliamperes. So probability of current measurement exceeds 13 milliamperes is nothing but probability that capital X is greater than 13. So as we know, we have to first standardize this normal random variable into standard normal random variable. So here we take x minus mu over sigma is greater than 13 minus mu over sigma. This is nothing but standard normal random variable capital Z, and we substitute value of mu and sigma. Mu is 10, sigma is 2. So this is nothing but probability that Z is bigger than 3 by 2. 3 by 2 is nothing but 1.5, and using this property, probability that Z is greater than 1.5 is nothing but 1 minus probability that Z is less than or equal to 1.5. So now in the normal table we have to look for Z equal to 1.5. So we concentrate on Z equal to 1.5. So in this column below Z I have to find out 1.5. So 1.5 is here, and I require only 1.5. Z is less than or equal to 1.5. So 1.5 means 1.5 plus 0.00. So we have to concentrate on this intersection of these two, 1.5 and 0.00, which is 0.9332. So we substitute that value here. The area corresponding to Z equal to 1.5 is 0.9332 from the standard normal probability table. So that we substitute here, and we find that this is the required probability. Probability that current measurement exceeds 13 milliamperes is 0.0668. We are asked to find out this probability also. What is the probability that a current measurement is between 9 and 11 milliamperes? That means required probability is probability that capital X lies between 9 and 11. So first we standardize by subtracting mu and dividing by sigma. So this is equal to probability that 9 minus mu over sigma is less than x minus mu over sigma, which is less than 11 minus mu over sigma. And then we substitute mu equal to 10 and sigma equal to 2, and this is nothing but standard normal random variable capital Z. So if we simplify, this is nothing but probability that standard normal random variable lies between -1/2 and 1/2, and -1/2 is nothing but -0.5. So this we can write as probability that Z is less than or equal to 0.5 minus probability that Z is less than or equal to -0.5 using this property. Now from the table we have to look for Z equal to 0.5 and also for Z equal to -0.5. So Z equal to 0.5 is here, and this is the corresponding value. Just a minute. Okay. So for Z equal to 0.5 we have 0.6915 that we substitute here. For Z equal to 0.5 it is 0.6915, and then we look for Z equal to -0.5. So I have to go for negative values. Z equal to -0.5, so it is 0.3085, and the difference of these two is 0.3830. Also we determine the value for which the probability that a current measurement is less than this value is 0.98. So here we are asked to find out the value of current measurement X such that probability that capital X is less than X is 0.98. Okay, here we have to determine the value for which the probability that a current measurement is less than this value is 0.98. So we are asked the probability. We are given the probability. Which probability? Probability that current measurement is less than some value of X. Suppose X. So we are not given this value. We have to find out this value. So we have to find out the value of current measurement denoted by small x such that probability that a current measurement is less than this x is 0.98. So we are given the area and we have to find out the corresponding value of x. So we are asked to find the value of x of current measurement such that probability that capital X is less than small x is 0.98. So first we standardize this. Therefore probability that x minus mu over sigma is less than x minus mu over sigma is 0.98. Now this is nothing but capital Z, and here we substitute values of mu and sigma. So we obtain that probability that Z is less than x minus 10 over 2 is 0.98. So this is the area in terms of standard normal random variable. So we have to find out this value of Z. Now this value is value of standard normal random variable. So we have to find out from the table the value of standard normal random variable for which the corresponding area is 0.98. So in the standard normal random variable we will look for the entries which are closest to 0.98. So we search for values in the table which are near to 0.98. So here we have to find out the values which are closer to 0.98. So you can see I find out two values, 0.9798 and 0.9803. So both the values are near to 0.98, but if we want the value closest to 0.98, then you can see this value is closest to 0.98 as compared to this one. Difference of 0.9803 from 0.98 is 0.003, and difference of this value 0.9798 and 0.98. So if we take this difference 9798, this difference is 0.0002, and difference of 0.9803 and 0.98 will be 0.0003. So this value is closest to 0.98. Now we find out the corresponding z value. So this corresponds to, in the row it corresponds to z equal to 2, and if we go up to this point, so this is for 0, this is for 0.01, 0.02, 0.03, 0.04 and 0.05. This is under 0.05. As we can see here, it is below 0.05 and it is in the row corresponding to z equal to 2. So the entry corresponding to this value of area is z equal to 2.05. So we consider, so x minus 10 over 2 will be equal to 2.05. So the entry in the standard normal table closest to 0.98 is 0.9798, and this probability corresponds to z equal to 2.05. Therefore x minus 10 over 2 must be equal to 2.05, and from this we can find out value of x. X minus 10 is 2 into 2.05, that is 4.1. Therefore x is nothing but 14.1 milliampere. So the current measurement is 14.1 milliampere. So if we take current measurement which is less than 14.1, then the probability is 0.98. So we find out the value of current measurement such that probability that current measurement is less than this value is 0.98. Next example. The breakdown voltage of a randomly chosen diode of a particular type is known to be normally distributed. So here voltage is the random variable under consideration, and it is given that it is normal random variable. So we are asked to find out the probability that a diode's breakdown voltage is within one standard deviation of its mean value. So we have to here the random variable is nothing but breakdown voltage, and we are asked to find out the probability that this capital X is within one standard deviation of its mean value. That means capital X is smaller than mu plus sigma and capital X is bigger than mu minus sigma. So this if we consider capital X in this interval, then we can say that capital X is within one standard deviation of its mean value. So probability that capital X is within one standard deviation of its mean value is nothing but probability that capital X lies in this interval mu minus sigma to mu plus sigma. So you can see in this figure, this is the normal probability curve. This mu is the mean, and suppose this distance is sigma, then this is mu minus sigma and this is mu plus sigma. So we are asked to find out the probability that capital X lies between these two values, mu minus sigma and mu plus sigma. So this shaded area is nothing but probability that capital X lies between mu minus sigma into mu plus sigma. Now this capital X we have to first standardize. So we subtract mu and divide it by sigma. So mu minus sigma minus mu over sigma capital X minus mu over sigma and mu plus sigma minus mu over sigma. So if we simplify, we can see this mu will cancel out and we have minus sigma over sigma. Here also mu will cancel out and this we replace by capital Z. So this is nothing but probability that standard normal random variable lies in open interval minus 1 to 1. So this we can rewrite as probability that Z is less than or equal to 1 minus probability that Z is less than or equal to minus 1. Now we use the table. First we find out probability that Z is less than or equal to 1. So here we have Z. So it is 0.8413. So we substitute this value 0.8413 minus probability that Z is less than or equal to minus 1. So we have to go for negative values. Z is less than or equal to minus 1. So this is the value corresponding to minus 1, 0.1587. And the difference is 0.6826. So the value of this area is nothing but 0.6826. So the probability that X lies within one standard deviation of its mean value is nothing but 0.6826, or this value of this shaded area under the curve is 0.6826. Now this is not only true for this random variable under consideration, breakdown voltage. This property is true for each normal random variable. So it is not only true for this problem only. This property is always true for any normal random variable, that the probability that normal random variable lies within one standard deviation of its mean value is always 0.6826. Similarly, we can find out the probability that X is within two standard deviation of its mean value. So that is nothing but capital X lies in between mu minus 2 sigma to mu plus 2 sigma. So if we standardize, we have to subtract mu and divide by sigma for each of these three values. So if we simplify, mu will cancel out. Here we will have minus 2 sigma over sigma, that will be minus 2. This will be Z, and here also we will obtain 2. So this is equivalent to probability that minus 2 less than or equal to Z less than or equal to 2. So this we can write as probability that Z is less than or equal to 2 minus probability that Z is less than or equal to minus 2. And using table we will find that the required probability is 0.9544. So the probability that X lies within two standard deviations of its mean is nothing but 0.9544. Similarly, we can find the probability that X is within three standard deviations of its mean. That is nothing but probability that mu minus 3 sigma less than or equal to X less than or equal to mu plus 3 sigma. And that is in terms of standard normal random variable. Z lies in open interval minus 3 to 3. So using this property and standard normal table, we will find out that required probability is 0.9974. So these three observations are true for each normal random variable, and some books are considering this as empirical rule. The results of above example are often reported in percentage form and referred to as empirical rule. So we can summarize the results of this example in this way. If the population distribution of a variable is approximately normal, then roughly 68% of the values are within one standard deviation of the mean. we have seen that probability that x lies in mu minus sigma to mu plus sigma is 0.6826. That means 68%. So 68% of the value lie 68% of the values are within 1 standard deviation of the mean. Similarly, 95% of the values are within 2 standard deviation of the mean, and 99.7% of the values are within 3 standard deviation of the mean. So we can represent in this graphical form also. This is the value of mu, and if this distance is sigma, this is going to be mu minus sigma, this is mu plus sigma. This distance is mu plus 2 sigma, so here mu minus 2 sigma, and so on. So 68% of the values are in between mu minus sigma to mu plus sigma. 95% of the values are in between mu minus 2 sigma to mu plus 2 sigma, and 99.7% of the values are in between mu minus 3 sigma to mu plus 3 sigma. So in this way we can apply normal distribution to real world problems also. So this is all about today's session. I hope you like this lecture. Thank you very much.